About our this new spectroscopic approach to probe quantum materials. This is um, this work is largely funded by DOE, and my salary is paid through the early career program. So I'm gonna begin by reminding you the limitation of current electronics, in the sense that the speed, in the sense of speed in signal processing and things like that. As you know, these familiar devices, one of the fundamental limitations could be the finite relaxation time of the carriers in their conduction band. And they are generally powered by battery. And because of this finite relaxation time, which is typically nanoseconds, of course, it depends on the materials, but there you have your gigahertz oscilloscope trace. So instead, if you could power devices with the electric field of a laser light, which is depicted here, and has both the positive and negative polarity, just like in batteries, then you could have much faster devices, simply because you could potentially change the population of carriers in these bands in very fast time scales, like in the femtosecond time scale, because the optical, because the laser light is the optical wavelength range, and there you could potentially have your femtosecond transistor. Okay, but to be able to do that, you need to understand how the materials react. How what is the fundamental response of the solid material to such a very strong fields. And it turns out that such a strong field response has been actually largely explored in the gas phase using in atomic and molecular systems for a long time now. One of the ways is the process of producing high order harmonics from the atomic and molecular targets, which this process we'll discuss a lot in detail today. In these experiments, you shine a fairly strong laser, typically at around 800 nanometer, to your gas jet, and you measure high order harmonics of the laser, kind of like this spectrum, and you use this spectrum to perform the spectroscopy. In the case of solids, though, because this required using fairly strong laser pulses, there has been a lot of issues on damage. So instead of doing such spectroscopy, the community actually focused on focused more towards micro machining and things like that in the case of solid materials. Until relatively recently, in an experiment where we were able to get into a very similar regime as in the atomic and molecular case in this experiment. This is experiment that we did, and the results came out in 2011. One of the co-authors is David Rees, sitting in the audience. So the way we were able to get around to this damage issue was that instead of using the typical 800 nanometer laser pulses, we used fairly long wavelength laser, like at the 3 micron wavelength range. And because of that, the photon energy is very far from the band gap, and this is a very strongly non-resonant excitation, and therefore you can reach similar level of peak intensities as people have been doing these experiments in the gas phase. This is one of the representative spectrum where we saw harmonics, high order harmonics up to 25th order, and a nice crystallographic orientation dependence. And it was zinc oxide crystal that was used. So that experiment sort of sparked interest in the community to use this type of high harmonic spectroscopy to understand materials, to see actually the potential. What can we do in materials? So in today's talk, I will start by briefly telling you about the spectroscopy in the molecular case, and then I will mention our recent the progress that the community has made since this first experiment on the zinc oxide crystal. And the most interesting part that I'm excited about is our the latest results on topological materials, bismuth selenide, and part of the reason these materials is interesting is because of this very interesting electronic band structure, and we are interested to see whether the strong field response on these materials are fundamentally different, and if so, how, and we can use this spectroscopy as a tool to do the spectroscopy on them. This is the gas phase process, the high harmonic generation process, which was understood in the early 90s using this semi-classical three-step model. I will take a couple of minutes to remind you about this. So this is the Coulomb potential of the electron that is bound inside an atom. The atom is subjected to a strong laser field. The half cycle of the laser field is shown here. And because of the high strength of the laser field, the Coulomb barrier of the electron is suppressed significantly. And as a result, the electron could now tunnel through this barrier. And since the strong electric field is still present, the electron could get accelerated in the laser field. And during this process, the electric field actually turns around, and therefore the electron would have to also turn around and come back. And with some probability, it could find the exact same parent ion that it came from and would then coherently recombine. So in this process, the lots of kinetic energy that electron has acquired in this acceleration that has to go in the form of this high frequency radiation upon recombination. Okay, and this there is a maximum amount of photon energy that you could expect, which is given by this very simple relation, essentially telling you that the conformative energy, the free electron cycle average energy of the electron in the laser field is essentially what gives you the upper limit in the high energy photon. And of course, in typical experiments, laser pulses have many cycles like this, and what you actually measure is the interference of such emissions from every half cycles, and that give rise to these discrete harmonic peaks. And this is the upper limit, for example, shown here, and it could go to a couple hundred and even to couple hundred EV or even to kilovolt. So here I just want to give you one example of how this process has been used in this community to do the spectroscopy of molecules. Here, this example is one of the first experiments that was done in Paul Corcom and David Boulanier's group at NRC. So this is done in nitrogen molecule, which is a diatomic molecule, and you can align this molecule with the laser field, and then do the strong field ionization and measure the harmonics. And importantly, because these molecules have interesting geometrical shape, and they also have interesting, the electronic orbitals with interesting shapes. They have angle-dependent response to the ionization as well as to the recombination efficiency. And using that as a tool they were able to sort of extract the shape of the electronic orbital in the molecule. So we wanted to understand what if there is a similarity or differences between the atomic response and the solid state response as good as we can. And this is one of the experiments we did, and it was done by our student towards Ghimire, who graduated last year. So here he grows solid argon film, which you see here. You see Newton's rings representing the different thickness of solid argon on the core surface. And he produces high order harmonics. And in this spectrum, in this plot, what he has shown is the high energy cutoff, the upper limit of the photon energy, as a function of the laser intensity. So here in the gas phase, he produces this nice straight line as predicted from this semi-classical model. But in the solid, there is something really interesting and more complex that occurs. And especially, I would like to point you to this abrupt scaling, which is when you hit certain intensities in this, all of a sudden you start seeing many harmonics in the form of another plateau like PHR. So in that sense, you can see that the solid state response is fundamentally different, and we have spent some time to understand this. And it turns out that there is a lot, depending on the materials and things like that. But in a very simple picture, this is what you could expect. This is a very simple representation of my solid, which is basically densely packed atomic periodic array of atomic sites. And this is a very simple picture in the framework of the electronic band structure. And this is the valence band, conduction band. So what happens is when you have a strong field present, the electron gets tunnel ionized from valence band to the conduction band. Then this electron gets accelerated in this conduction band, and so does the hole in the valence band. And there are two major possibilities. One is this nonlinear, this driven current in the band could radiate high frequency photons, and the other is the recombination of this electron with the hole could also release this difference energy in the form of high energy photons. So we can look at this in more detail so everybody can understand. So essentially, this is very similar to the gas phase in that this is also a three-step process. In the first step, the electron gets tunneled through the band gap, leaving behind the hole, and the electron gets accelerated in the field, and so does the hole, on their respective bands. And at some point in time, and the crystal momentum, this electron could recombine, right? So step one, tunneling, number two, step two, acceleration, and finally in step three, the difference energy of this electron and hole at these bands could give rise to this high frequency radiation. So what you can see here is that if you look at the instantaneous position of these electrons and holes, during this acceleration time, you could see that so these electron and holes at these different positions, they could also recombine at and there the difference energy would be different from if they were to recombine at a different place in the Korean zone. So what this means is in the spectrum, you're measuring different harmonic orders corresponding to different photon energy, and you can kind of already see from here that if you had a way to measure the emission time of these high harmonics, then you had a way to probe the this crystal momentum dependent band gap, right? So that's one type of spectroscopy that you could potentially do. So this is likely the first experiment where we actually saw some signatures of the electronic band structure in the harmonic spectrum. We started with magnesium oxide crystal. This work was led by Yongxing Yu, who was a postdoc in our group. So this is the band structure of magnesium oxide crystal, which looks, very complicated. This is a relatively simple case, being a cubic structure, but you can take advantage of the polarization, and for a linearly polarized laser field, you go through some selection rules and find out which bands are supposed to be coupled. And there are three these major bands, and at least what I'm going to tell you today is that there were some portion of the spectrum in the measurement that we were able to attribute to certain pairs of bands, like that. And since this this experiment, there has been a lot of interest, and other groups have done similar work. I'm actually taking this to a new level. For example, measuring the density of the states and the singularities in the band structure and things like that. Okay, so since solid does sound like a complex system to understand the strong field driven processes, we wanted to have something, and gas is well known, so we wanted to have something in between. And these 2D materials, two-dimensional crystals, are sort of an intermediate state, states which could connect both sides. In particular, this MOS2 crystal, has been studied a lot by the group of Tony Hines and others. For example, they have used second harmonic generation to measure the atomic scale structure of the surface, and we decided to also study high harmonic generation in the strong field limit using this platform. So the idea here is very similar to the gas phase, at least how I thought at the beginning was, let's say if you had exciton in the system, which for this discussion, essentially the electron and hole, they are bound together, right? And in presence of the strong laser field, because of the different charge, the electron could go in one direction, and the hole could go in the other direction. In the subcycle time scales, they could come back at the same place, and they could potentially recombine. Upon recombination, just like in the atomic case, they could produce coherent light, and which we could use to do the spectroscopy that we want. So that was the idea. This is the first one of the first results in MOS2. What you see here is the harmonic spectrum, first from the bulk of MOS2. These are a few harmonics, and this work was led by Hangzi Lu, who also graduated. When you put in the single isolated layer in the setup, then you measure also harmonic spectrum, but with this spectrum gets much more interesting. As you can see, you first start to see more harmonic orders, and you also see additional even order harmonics, which are not present in the bulk, and this even order harmonics are consistent to the broken inversion symmetry that you have in the case of monolayer. So this was a very nice way for us to make sure that the target does have the single isolated layer. There were lots of interesting features on the spectrum, but today I'm going to tell you one of those features that at least I was very excited when we saw it. First, this is the crystal structure, which is hexagon, and we measure the crystal orientation dependence. So that was not the exciting part. But what was really exciting is that when we measured the polarization of the harmonics, and we found out that these even order harmonics are actually polarized orthogonal to the driving laser field. So in the gas phase, the harmonics are always polarized in the same direction as the laser field because there is no dipole to radiate in the other direction, right? So this was pretty remarkable that when you have a periodic array of atoms forming a crystal, it gives rise to something fundamentally different. We understood this by using this simple picture, which is essentially you write down the equations of motion in the band, for example, this is the group velocity, which is typically it is given by the dispersion, and this another term which has this Berry curvature. Typically, you don't see these terms. You typically neglect this because it is much smaller than the dispersion. But in our case, since the applied field was very strong, this term was actually comparable to the other term. What it does is that, as you can see, because of this cross term, it sort of acts like an artificial magnetic field for the electron in the band. So, if you remember your Hall effect experiment, it acts like, as in the Hall effect, you have the Hall voltage that, of course, in the perpendicular direction of the applied voltage and the magnetic field. So similarly here, this Berry curvature gives rise to this nonlinear current in the out of plane direction, and that could be a source of this orthogonal polarization in the harmonics. With that understanding, we recently went a step further on this, and I started looking at the topological materials. As you might know, one of the signatures of topological materials is these topological insulators, especially is the conduction. The bulk has the band gap, but the surface has this interesting Dirac-like bands without dispersion, and we're interested to see, what is if there is a fundamentally new on how this band could respond to the strong field, and if so, if we can understand this, and maybe there is a new way to do the spectroscopy on these topological materials. So there's lots of theory work going on. For example, looking at the different efficiency of harmonics in the 1D model, using 1D model, and another work is by they predict that by measuring the ellipticity, how the ellipticity of the harmonics with respect to the driving laser field changes, and using that, they predicted that we could retrieve the topological invariance on these systems. So we were able to realize this in experiment using one of the well studied topological insulators, bismuth selenide. It is because it has a relatively large band gap, and we were able to produce fairly strong laser pulses in the range from 5 to 10 micrometers. So you will need at least 2 photons to cross the band gap. And the measurements are done in in thin films in the transmission geometry, as well as using the bulk in the reflection geometry. This is one of the representatives of harmonic spectrum. Kind of looks very similar to what you saw in the first zinc oxide experiment. Here harmonics are up to 15th order. And interesting non-perturbative behavior. So we spend a lot of time to analyze the spectrum and crystal structure. So what I want to give you a message here is that if you look at the spectrum carefully, you can see some even order harmonics very similar to in the case of MOS2. And in this case, this inversion symmetry, because this is a bulk, and this is the bulk does not have the bulk has the inversion symmetry, but the first quintuple layer, essentially the surface, has the inversion symmetry broken in many orientations. So this we attribute these even order harmonics, are coming from the surface states. We do very similar polarization resolved measurements like in MOS2, and here also. The harmonics, the even order harmonics are polarized in the orthogonal direction to the laser field and to the order harmonics. So we have a theory to describe this the generation. Basically, I'm not going to go through all the details, but this is a 4-band model where 2 bands correspond to the bulk and 2 bands to the surface, and we can solve semiconductor block equations by selecting these bands, and we can calculate what is the contribution from the surface and what is from the bulk. And as you can see, bulk has the odd harmonics in regardless of the orientation. The surface has additional even order harmonics, and that actually depends on the orientation. In certain orientation, you can actually enhance the even orders, the strength of the even orders, which is what we also observed in the experiment. Okay, so just one more thing on the spectrum. If you were to ask, what is the signature of the topological nature of the surface states? So this is one of the signatures here. Especially, it becomes very clear in the case of circularly polarized driving fields. This is the experiment where you basically look at the harmonic intensity. You pick one of the harmonics and measure the intensity as a function of the polarization of the laser field. You change from the linearly polarized to slowly to the circularly polarized case. These are the results from MOS2, which is topologically trivial. And these are results from bismuth selenide, which qualitatively they look completely different, as you can see. And the picture here is very similar to the atomic-like picture, but here we attribute this, especially this strong emissions at circularly polarized case to this Dirac-like bands. And for example, where you have the vortex-like features in the dipole matrix elements, when you consider when you plot the dipole matrix elements. So this is one of the very clear signatures that appears in the circularly polarized laser fields. And we can do the calculations for the circular field. So essentially. This is the PG plot. What we have been doing is we are trying to separate the contributions from the surface and the bulk. So 2 bands of the surface and 2 bands of the bulk, and use the theory to help us to really distinguish the contributions from the surface and the bulk. Okay, I'm gonna just take 1 more minute maybe. To tell you what we have planned to do next. So since we sort of found out the signature of the topological surface in our harmonic spectrum, we want to use this as a tool to actually measure phase transitions in materials like this wide semimetals, where for example, Aaron Lindenberg and his team has done something really fantastic in terms of using lasers and changing the phase, the quantum phase on these materials, and we want to be able to produce harmonics, and these are preliminary data of harmonics, and actually use these harmonics as a way to sort of to probe these various phase transitions. And if that becomes successful, then we could do something fancy. For example, testing this theory, which is here they claim that that by using circularly polarized laser fields, you can break time reversal symmetry on these materials, and produce a replica of these wide points. And something more fancy here, using two different circularly polarized laser fields in two different planes, you could actually tune these wide points in the Brilliant zone just like that, and we hope to be able to do test this theory in the near future. With that, I would like to summarize my talk, because we have another talk coming. What I told you so far is I introduced you to sort of the high harmonic spectroscopy technique, which was used in the atomic and molecular case, molecular systems for a long time. And we were able to produce harmonics from solid materials without damaging the sample. And there is lots of exciting things in terms of understanding the mechanism and probing the materials with these harmonics. And this could be a potential probe for in the future the light-induced quantum phases in materials. And with that, I would like to thank my team and thank you for your attention.
I had a very naive on the slide just before this. You one more. There was like when you were showing a plot about an equilibrium plot. Yeah. Why are you saying you reach an equilibrium when the shear displacement is reaching zero, when the thing is still dropping? Why is it not like a 2? Or do you understand what I'm asking? On the plot on the lower left.
Mm-hmm.
Yeah. Why is the equilibrium point there?
I think this is the work from Aaron Lindenberg, so I'm not fully responsible. But when you start, the system does not have the inversion symmetry, and then when you pump, you introduce strain and between these different layers, and then essentially right. So and then you watch this as a function of the time delay, for example, yeah. So it's about how wide this is equilibrium. I'm not sure. I'm guessing this is the state where they start from.
All right.
But yeah, it's for them.
In the interest of time, we should actually move on to our second speaker. Thanks. Okay, great. So our next talk is by Daniel Ranard, and I'd like to introduce Shelley Chi, who will be talking about emergent classicality in multi-partite state mechanics.
Great. So I'm going to start by asking a very general question, which is what sort of things can happen during a quantum time evolution? So we have some input state, And then we have some dynamics, maybe it's unitary dynamics, maybe it's sort of open system dynamics, meaning that maybe we add degrees of freedom, maybe we discard some degrees of freedom, and then we get some output state. And in particular, I want to be asking about when the output system has many degrees of freedom. So you can imagine that we take a qubit, we couple it to a lot of qubits, we let them evolve, and then we study all of those output qubits. And we can ask what sort of things can happen during this evolution. In particular, how can information spread during this evolution? And there's some constraints on how the information can spread that I'm sure you already know. For instance, no cloning. So you couldn't have the qubit A have all of its quantum information appear both at the first and the second output. Another sort of constraint that you'd be familiar with is that you can't have one output contain a copy of the input measured in one basis, and then have another output contain a copy of the input measured in a different basis, if those are incompatible measurements. So those are just two sorts of familiar constraints that we have on information spreading. And I'm going to be talking about a new result that gives another sort of constraint. So I'm going to be talking about a new theorem that quantifies how information can spread. And it's sort of in the spirit of no cloning, but it's a generalization in a sense. So this will apply to any quantum time evolution. So in that sense, it's very general. And I'll mention several examples later on. And one of the reasons that, at least I think this is interesting, is that the specific result is going to tell us something about emergent classicality. So what I mean is that we're going to see that any quantum time evolution on a large system will exhibit some properties reminiscent of decoherence or classicality. And that's what I'm referring to as the emergent classicality, and I will justify that shortly and explain exactly what that means mathematically. So first let me say, this is based on some similar ideas in this earlier paper, which is really nice. And then we have a much stronger result with a more constructive argument. So again, I'm going to be talking about an input system A, and then imagine that we couple it to an environment B, and that environment B has a lot of different parts. We evolve them together, and then let's ask, what does a single observer at a single one of these fragments of the environment see? So this guy, Bob, at B3, what can Bob learn about A? And of course, if I don't tell you exactly what this evolution is, you don't know exactly what Bob can learn about A, but in fact, you can make a very general claim, which is that for almost all of these Bobs, for almost all of these BI, they can only learn classical information about A. And the classical information they learn about A must be obtainable from some fixed measurement of A. So this is a punchline that I'll increasingly clarify in the next couple minutes. Almost everywhere in the environment, any locally accessible information about A must look classical in the sense that you could have obtained it from some fixed measurement on A. And that measurement is independent of which output you're looking at. So let's start making this a little more explicit. We have our input state rho A, and then we're going to bring in the system B in some initial state. We're going to evolve the joint system. And then to focus on a single output system, we're going to trace out everything except this one system BI. So we're throwing these other systems in the garbage. And this evolution from rho A to rho BI, that's the evolution that I'm going to characterize as classical in some sense. And for me to be able to do that, I need to introduce a little more jargon about quantum time evolutions in a general setting and what it would mean for one of those evolutions to look sort of classical or to implement some measurement process. So for that reason, let me remind you that a quantum channel from a system A to B is just a map on the set of density operators. So it sends one density operator to another. And it could be unitary evolution, or it could represent some sort of measurement process. Now, a very special type of quantum channel is something called a measure and prepare channel. So that's a channel that you can express with an expression like this, where these M alphas you can think of them, they're measurement operators, really they're POVM operators. But if you're unfamiliar, just think of the example of them being orthogonal projectors. So what this evolution is, I'll blow this up, it looks like we're taking our input state, we're measuring it in some, maybe an orthogonal basis, and then contingent on that classical outcome alpha, we're gonna prepare some state on B that depended on alpha. And this is a very special type of evolution. It's the sort of thing that if Alice and Bob were in different labs, they could implement this sort of evolution by only sending classical information. Because Alice would measure these M alpha basis, measure in the M alpha basis, she would get some outcome alpha, and then she would send it along as a classical piece of information to Bob, who would then prepare state sigma alpha. So with this background about what it means for an evolution to be sort of classical in the sense that it looks like a measurement happened, let me go back to our setup and introduce the main claim here, which is that this evolution from row A to row BI, for almost all of these output systems BI, it will look like one of these classical evolutions. It will be approximately one of these measure and prepare channels that take this form that you just saw on the last slide. And the measurement that is used, it depends on what our channel is, but the measurement used will be independent of which output we're looking at. So for almost all of these outputs, what they see from A looks like we measured A in some fixed basis and then prepared some state based on it. So that's just repeating that idea. Okay, before I get into a more precise statement, let's just talk about some examples. So the same setup I was already talking about, but now let's talk about some specific evolutions. So in this first example, it's sort of like a decoherence setup. So just focus on this unitary here. It's going to take, if A is in the 0 state, it's going to take everything to zeros. But if A is in the 1 state, it's going to take everything to ones. And maybe this should be a 0. I might need to fix that. But what this is going to do is, if we look at the output row BI, it's going to look like it was measured. It's going to look like row A was decohered in the 0, 1 basis, and then that outcome got distributed to every single output, and then this is the final state. So in this case, it very trivially satisfies the theorem that I was talking about, because every single one of these evolutions, A to BI, is going to look like a measure and prepare channel. Here's a very different example that will also need to satisfy the theorem, where we're going to use an identity channel. So again, just focus on this U here. We're going to send the 0 state to all zeros, and we're going to send the 1 state to something that has a 1 on this first output of B. So if we look at the evolutions to subsystems, we have row A just going, it ends up at row B1. It's like we sent the entire qubit A to the first output. So that's not a measure and prepare channel, but the theorem is only going to claim that almost all of the BIs that have a reduced channel that looks like the measure and prepare channel. So this will also satisfy the theorem. Because although the first output of B learned about A, the rest of them didn't learn anything about A. Okay, and then one more sort of physical example is, imagine that we have a spin chain that's a spin chain B, and then we bring in this extra qubit A, and we attach it to the spin chain, and then we start evolving them with our local spin chain Hamiltonian. So I can't write down analytically for you what these evolutions are going to look like from A on the subsystems of B, but you can do numerical examples, and you can check that indeed it's true. For almost every output BI, this evolution is going to look like one of these classical type evolutions. Does anyone have any questions so far? Be happy to take them. Okay, so let me just draw a picture of what this general result is. So again, we have our A, we couple it to all these B, And then we look at just these output systems B. So maybe think of the spin chain example again. We're looking at subsystems of the spin chain environment when we couple a qubit to the spin chain. And the claim is that there's going to be some region that I'm calling Q, some excluded region, but then and there's going to be some order 1 finite region. And then for every other region R, for every other local region R of this output, the evolution from A to R will look approximately measure and prepare. So this theorem is weak in the sense that it's not going to tell you what the evolution from A to Q looks like. But it's strong in the sense that Q is some order 1 subsystem. And then for literally everywhere else, if we look locally anywhere else on this big spin chain, no matter how big that spin chain is, the evolution from that input qubit to one of these local regions on the spin chain is going to look like one of these classical type evolutions. So I'm not going to dwell on it, but let me flash up what the mathematical statement would look like.
Question?
Yeah, sure.
Can you tell anything about the entanglement between the different subsystems of B from your theory? Like, for example, how B1 and B2 are entangled, or how Q and R are entangled. Like, how much can you tell?
So in the setup of this statement, we're sort of singling out an input system A, and then the rest of the spin chain is the output systems. So it's made to tell you about how A is entangled with the output systems as opposed to how the outputs are entangled with themselves. But you could sort of reconfigure this statement, and instead you could choose a different qubit on your spin chain to be the input, and then you could evolve the whole spin chain and think of the rest of the qubits as the output. So for any qubit, for any spin of your choice, you can think about its entanglement with the rest of that spins using this idea.
The measure and prepare, when you're saying, you're saying like if I'm looking at, can there be more than one R? Can there be like an R1 and an R2 and I can look at them? Or is there only just one R?
Yeah, so what this theorem is going to say is that really for all R that don't overlap Q.
Okay, good. So then what I want to know is like, when you're saying measure and prepare, if I would look at one of the R's, it would be like A picked spin down, and then I evolve the subregion R B from that spin down. The next time I measure R, A is still spin down. I mean, with the exception of some noise from time evolution, but you can't get a scenario where you can look at multiple R's and get inconsistent A's. Projections.
I might want to try to address the exact question after, but maybe I can say that for every R, the evolution from A to R will look like it's using the same measurement on A.
That's what okay.
So,
yeah.
and that's an important part of the
Yes.
result. Yeah. You're
What's the intuition that the result gets worse when you increase the size of R?
Oh, sure. So, because this result is really about constraining what information in the outputs are locally accessible. So for small regions R of the output. Whereas once you start looking at really large regions of your spin chain to try to extract information about that initial qubit that you attached, when you're looking at really large regions, it's a much crazier problem because quantum mechanics can store information in weird ways on large regions. Maybe that's a little vague, but
I guess if I think to each small R I do measure and prepare, it's kind of surprising the same measurement.
Right.
Is it not surprising that to the union of those regions, I don't have measure and prepare, even though I'm using the same measurement for each small region?
yeah, so the idea is that if you're an observer on R1 and you don't know about anything else going on and you just look, what did I learn about A? It looks like this classical measurement happened. And if you're an observer on R2, same deal. But if you start combining if you add up lots of regions, R1, R2, R3, and look at the combined output, the evolution could be hiding quantum information in weird ways distributed among the different systems, even though you couldn't locally see that information.
Another question. Suppose I know, like, what I can know about B1 and what I can know about B2. how much can I tell about B1, B2 from your state?
I would need to think a little bit more about how to answer that. Yeah. Okay, so let me talk a little bit about this excluded region Q that I'm calling the quantum Markov blanket, because I think it's a sort of physically significant idea. So the idea is that for any evolution from this one qubit, we couple it to the spin chain, we evolve them, and now I'm going to be able to identify this finite size blanket Q. Why am I calling it a blanket? So on one hand, that's sort of a term from the statistics literature, but it sort of makes sense here in the sense that any information about A that you can access any information about A that you can access locally can be obtained from a classical measurement on just Q. So in that sense, Q is sort of blanketing A. And if you want to learn about A, you can just learn about Q instead. It's sort of a blanket that holds all of the information about A. That's how I like to think about it. And the sort of neat thing is that no matter how big your spin chain is, you have this order 1 size blanket that contains, in a sense, all of the information about A. Actually, before I try to sketch any of the argument, I'd be happy to take any more questions.
Q grows the longer your time evolution is or something? Presumably.
Yeah, so you might think that as you time evolve your system and there's some sort of effective light cone, the information from, if it's a local time evolution, the information from A can only spread so much, but then it's spreading onto a larger and larger region, and that's your intuition that you're going to need a larger and larger blanket. But the amazing thing is that actually no matter how long you time evolve it, the blanket at some finite size, you won't need to take it much larger. You can truncate it at some finite size and get a good result. And that's because even though in some sense the quantum information keeps spreading through this spin chain, the locally accessible information will need to disappear, or the regions where you have locally accessible information will need to be very restricted.
If it were like a fully scrambling channel,
Yeah.
Could Q be of 0 size?
Exactly.
Okay.
Exactly. So a fully scrambling evolution will be such that there's no locally accessible information about A, as you know, and therefore you can even take Q to be 0.
Does Q depend on the state? Does Q depend on the initial state of A?
No. Okay, so I'll just say a few words about what sorts of techniques you can use to possibly prove something like this, especially because part of the argument I think actually gives you some good physical intuition for what's going on. But the very first step of the argument is to use this thing called channel state duality. So whenever you're talking about quantum dynamics, you can equivalently be talking about some sort of associated state. And properties of the state will map onto properties of the dynamics. And very specifically what I mean is that if you take this channel NAB, N from A to B, and then you take an auxiliary system A prime, and you insert a bell pair, and then you act the identity on A prime, but on A, you do the channel. So basically you take a bell pair and you throw half into your evolution, you throw half into your experiment. And now you look at the joint state between the auxiliary system and the output B. This joint state, in some sense, captures everything you could ever want to know about this channel, about this evolution. So instead of studying the channel, we can just study this state. And that's a useful technical tool because it means that, because often we're very familiar with how to talk about states and their entanglement, and we're a little less familiar about how to talk about the dynamical correlations in channels. And if a channel is measure and prepare, that's equivalent to the associated state being a separable state. So we've translated this theorem into this state framework, and instead we're going to have a theorem about states that we prove instead of a theorem about channels, but it will be equivalent. So first, here's some preliminaries. Maybe this first one you're familiar with, the second one, the mutual information, you might have seen before. This one you might not have seen before, so let me emphasize it. This is the conditional mutual information. So if we have three regions X, Y, Z, then we define this quantity here, which can be written in terms of entropies. And the words you should tell yourself are, this is telling you how much more knowing YZ tells you about X than just knowing Y would tell you about X. So with those definitions, here's the sort of equivalent statement that we're going to prove for states instead. And it's that whenever you have so now it's just a theorem about states. And it says whenever you have a state on A and then many subsystems B1 to Bn, there's some region Q, which you can think again of as the blanket of A. And this region Q is going to be such that we have this conditional mutual information being small. And what this means, if you follow the words, is that the amount you learn about A by knowing Bi and Q is not much more than the amount you already know about A from just knowing Q. So that means that this special region Q, this blanket, already tells you basically everything there is to know about A. And if you also ask, how much more do I know when I add this system Bi, it's going to be a very small amount. So this is the sort of theorem, the sort of warm-up theorem that you prove before proving the result that I'm advertising here. And don't worry, I'm not going to try to prove the result, but I am going to flash the slide, and maybe someone watching the video one day will pause it. So the takeaway from this slide should be that there's actually a constructive algorithm for building up this Markov blanket Q. And you can use it in numerics. So I do spin chain numerics with exact diagonalization, and I have 20 qubits, and I couple my 1 qubit, and then I evolve. And then I ask, where did the information go? What is the blanket that covers this input system A? And you can actually constructively build up this Q, just sort of figure out where the information went. And here is the algorithm for building up this region Q. A key element will be using the chain rule of mutual information and also using strong subadditivity. So people in quantum information theory often say that any slightly non-trivial theorem probably used strong subadditivity. So that's true here as well. It's sort of one of the main technical results in the quantum information theory, a basic result. Okay, and let me also flash up here this sort of visual proof that you can find in the paper. So the words that go with this are, to find this region Q, this Markov blanket, we're going to build it up qubit by qubit. So think of the spin chain again. We're going to first look for the qubit on the spin chain that knows the most about the input A. And then we're going to expand that region and find the next qubit that knows the most about the input, given that we already know about that first qubit. And you end up sort of optimizing over the space of paths through subsets. And there's this sort of flow argument that you can find in the paper, which tells you that there's this sort of bottleneck in the flow, and then that tells you what the blanket is. And I won't try to go more into that right now. So stepping back from the proof, let's review the main result here, which I think is actually pretty simple. And the main result is that whenever you have a system A interacting with a large environment, then almost anywhere you look in the environment, the evolution to that subregion will look like we've done a classical measurement and then prepared some state based on the outcome. And this is my last slide, suggesting some future work. So the fact that you have a constructive method, to me, is sort of suggestive that you could use this idea to make more efficient classical simulations of quantum many-body systems. Because one of the outputs of this algorithm is that you're sort of finding the basis in which subsystems are internally decohering with other subsystems. And by finding that basis, you might then try to measure it in your classical simulation in order to break entanglement and then have a more efficient simulation. That's just an idea that I have. And then more concretely, you could ask how tight the bound is, and can it be any better when we assume something about spatial locality? In all the results I've been talking about, we didn't assume anything about spatial locality of the Hamiltonian generating that evolution. So maybe if you do assume something like that, you're going to get a much stronger result. Okay, thanks.
Oh, you said that Q was of order 1 size. I assume you mean like in the total system size. And is that
Yes.
right as well?
Yes.
Okay. You just would choose a larger Q if you wanted the error to be small. But like, of what size? Like, is Q like for any channel and for any system size? Can I pick it to be like 10?
Yeah, yeah, good comment. So maybe R is 1 and Q is 10. We can choose that in the setup of the theorem. And now we'll get something like only 10% error. And it doesn't matter how big the spin chain is. It could be an infinite spin chain.
Okay, I see. For any channel.
Yep.
Okay.
The statement about states that you proved like 3 slides after this one, you said that was a warm-up, but what's left to prove after you prove that? It seems like that's enough.
It's a subtlety that I won't try to say right now, but I'd be happy to explain to you later.
Can the size of Q be somehow a measure of scrambling?
Yeah, if you ask how big do I need to take Q to get a good result, the theorem is saying that, oh, you only need to ever take it this big. But sometimes, depending on your channel, you could have taken it even smaller. Like when Chris pointed out that for a fully scrambling channel, you could take Q very small. So based on that intuition, I would say, yeah, that's a good idea.